This scene deals with the subject many fathers find so difficult.
Welcome to podcast VE 0.1, where we break down the latest research and tools for curious engineers. Okay, let's start with a thought experiment. Imagine a massive earthquake strikes off the coast, triggering a potentially devastating tsunami. You need to predict exactly where and when those waves will hit, and how big they'll be, to give people enough time to evacuate. Now, imagine your best prediction model requires 50 years of computation time, running on over 500 GPUs on a supercomputer. That's obviously completely useless for an early warning, right? The tsunami would have hit decades before you got the answer. Now picture this instead. That same critical prediction, the part you need right now after the earthquake happens and the first sensor data comes in, gets calculated in less than a quarter of a second. 0.2 seconds, to be precise, on a modest regular GPU system, not even a supercomputer. That colossal difference, a speed-up factor of about 10 billion, isn't science fiction. It's the core result of a fascinating paper titled Real-Time Bayesian Inference at Extreme Scale, a digital twin for tsunami early warning applied to the Cascadia subduction zone. So what's the underlying problem they're tackling? Predicting tsunamis generated by underwater earthquakes is incredibly complex. It's not just about simulating waves, it's about figuring out the source of the tsunami, precisely how the seafloor moved during the earthquake based on limited, noisy data from sensors on the ocean floor. And critically, it's not enough to just get a single prediction. For emergency responders, knowing the uncertainty in that prediction is vital. How confident are we about the wave height? What's the range of possible arrival times? This requires sophisticated statistical methods layered on top of already complex physics simulations. The researchers focused specifically on the Cascadia subduction zone, which runs along the Pacific Northwest coast of North America. This area is known to be capable of generating enormous earthquakes, magnitude 9 or even higher, posing a significant tsunami risk to cities like Seattle, Portland, and Vancouver. Simulating the 3D wave physics involved, specifically how acoustic waves and the slower gravity waves that form the tsunami propagate, and performing the statistical inference needed to estimate the earthquake source and predict the resulting tsunami for this region, involves potentially billions of parameters. Doing this brute force calculation quickly enough for a warning seemed computationally impossible, hence that initial estimate of 50 years on hundreds of GPUs just to get the most likely answer, let alone the uncertainties. So how did they achieve that mind-boggling speed-up? The core idea is building a, quote, digital twin of the Cascadia subduction zone. Think of a digital twin like a highly sophisticated, data-driven simulation model of a real-world system. In this case, it's a model that understands the complex physics of how acoustic and gravity waves travel through the ocean in 3 dimensions after an earthquake shakes the seafloor. This digital twin uses real-time data coming in from acoustic pressure sensors deployed on the seafloor. When an earthquake happens, these sensors pick up the pressure changes caused by the moving seafloor and the subsequent water movement. The system feeds this data into a Bayesian inference framework. Now, for engineers who haven't dabbled much in statistics, Bayesian inference is essentially a mathematically rigorous way to update our beliefs or understanding about something based on new evidence. Here, the something is the unknown spatiotemporal pattern of the seafloor motion. Exactly how, where, and when the seabed moved during the quake. The evidence is the pressure data streaming in from the sensors. The beauty of the Bayesian approach is that it doesn't just spit out a single best guess for the seafloor motion. It calculates a whole probability distribution, effectively saying, based on the sensor data, this pattern of motion is the most likely. But these other patterns are also possible, with these specific probabilities. This directly translates into quantifying the uncertainty in the tsunami forecast derived from that motion. Knowing there's a 30% chance wave heights could exceed a critical threshold is far more useful for decision-making than a single, potentially misleading number. But how do you compute this complex Bayesian inference involving billions of parameters and 3D wave physics in real time? This is where the breakthrough algorithmic innovation comes in, an offline/online decomposition. For software engineers, this concept should feel familiar. Think about optimizing a complex application. You might spend a lot of time up front during the build or compile phase, doing heavy computations, pre-calculating lookup tables, optimizing data structures, or training a machine learning model. This is the offline part. Then, when the application needs to run and respond to a user request, the online part, it can use those pre-computed results to deliver an answer very quickly. That's precisely the strategy employed here. The researchers identified a mathematical property of the physics involved. Specifically, the relationship between the seafloor motion, the parameters they want to infer, and the pressure waves measured at the sensors, the observables. This relationship exhibits something called shift invariance, which, simplifying a bit, means there's a certain regularity or structure in how changes in the source location affect the sensor readings across the network. Exploiting this specific mathematical structure is what allowed them to mathematically split the massive Bayesian calculation into two distinct parts. The offline part involves the truly heavy lifting. It requires simulating the complex 3D wave propagation from many potential source locations to each sensor. This involves solving complex partial differential equations that describe the coupled acoustic gravity waves, capturing both the fast-traveling sound waves and the slow-moving tsunami wave. This is where the supercomputers come in. They used a sophisticated simulation toolkit called MFEM, which is a software library specializing in high-performance finite element methods for solving these kinds of complex physics equations. They scaled this massive offline computation across nearly 44,000 GPUs on the El Capitan supercomputer, achieving an impressive 92% parallel efficiency. This is like a massive one-time compilation or pre-computation process. It takes significant resources, but you only need to do it once to prepare the system. The output of this stage isn't the final answer, but rather a highly optimized representation of the underlying physics and the relationship between any possible earthquake source and the resulting sensor signals. Then comes the magic, the online part. Once an actual earthquake occurs and the real-time pressure data streams in from the seafloor sensors, the system uses the pre-computed results from the offline stage. Because all the heavy physics simulation is already condensed and factored out thanks to that shift invariance property, the online component only needs to perform the Bayesian inference calculations using the incoming data and the pre-computed structures. And remarkably, this online step, solving the inverse problem to find the seafloor motion and forecasting the resulting tsunami, complete with uncertainties, takes just 0.2 seconds on a modest GPU system. That's the 10 billion-fold speed-up compared to the naive approach. It transforms the problem from computationally impossible to practically achievable for real-time warning. So what are the key takeaways here? First, the sheer scale and the achievement. We're talking about tackling a billion-parameter Bayesian inference problem tied to complex 3D physics, initially estimated to take decades, and finding an algorithmic way to get the crucial real-time answer in under a second. This highlights the immense power of mathematical insight and clever algorithm design, specifically the offline/online decomposition. It's a testament to how rethinking the computational structure of a problem can yield performance gains far beyond simply throwing more hardware at it. Second, the specific application is incredibly impactful. Focusing on the Cascadia subduction zone addresses a real and present danger. A reliable, near-instantaneous tsunami forecast system for this region could save countless lives. The use of acoustic pressure data from seafloor sensors, coupled with the sophisticated 3D physics modeling, represents a state-of-the-art approach to understanding these events as they unfold. Third, the incorporation of uncertainty quantification via the Bayesian framework is crucial. For engineers building critical systems, simply providing an output isn't enough. Understanding the confidence in that output is often just as important. This system provides emergency managers with probabilistic forecasts. Not just a 5-meter wave will hit here, but there's an 80% chance of waves between 4 and 6 meters hitting here within the next 30 to 40 minutes. This allows for much more nuanced and risk-informed decision-making during a crisis. How widely should they evacuate? Which resources should be prioritized? Uncertainty quantification helps answer these questions. Now, thinking like engineers, we naturally ask about limitations and next steps. How much does the accuracy, and perhaps even that 0.2 second speed, depend on the sensor network? The system fundamentally relies on the quality and timeliness of data from those seafloor sensors. The density and placement of that network will absolutely influence how accurately the system can pinpoint the initial earthquake source characteristics. The Bayesian framework is generally robust to some level of noise or missing data, but better input data will always lead to better, more confident outputs. The 0.2 second figure represents the computational time after the relevant data has arrived and been ingested. It doesn't include the time it takes for the physical waves to reach the sensors or for the data to travel back to the processing center. What about the shift invariance property that enabled the decomposition? This mathematical property was key to the speedup. Real-world earthquakes can be messy and complex. While this property proved effective for the modeled Cascadia scenario involving 3D acoustic gravity waves, its applicability might need further validation for different types of earthquakes or more complex geological settings. It represents a clever trade-off, leveraging a structural property of the physics to gain immense speed, potentially at the cost of some generality, although it seems well suited for this specific critical problem. And finally, how do we get this from a groundbreaking research paper to a system operating 24/7 in an official tsunami warning center? This research provides a powerful computational engine, a proof-of-concept digital twin. Transitioning it to operations involves significant engineering effort. Building robust, fault-tolerant data ingestion pipelines from sensor networks, integrating the system with existing warning protocols and communication channels, performing extensive validation against historical data and a wider range of simulated scenarios, and ensuring the system is maintainable and reliable under operational conditions. These are non-trivial steps, bridging the gap between research and real-world deployment. For us as software engineers, this work is exciting not just because of its life-saving potential, but also because it showcases powerful computational paradigms. The offline/online decomposition strategy is a pattern we see in many areas, from optimizing database queries with indexes, to pre-compiling code, to training massive AI models offline for fast inference online. This paper takes that idea to an extreme scale, applying it to complex physical simulations and Bayesian inference. It's a reminder that sometimes the biggest performance gains come not just from faster hardware, but from fundamentally restructuring the computation, exploiting the mathematical properties of the problem itself. It demonstrates how extreme-scale computing, often associated with long-running scientific simulations, can be intelligently harnessed through techniques like this decomposition to provide critical, real-time insights when they are needed most. The ability to perform Bayesian inference at this scale and speed, providing not just predictions but quantified uncertainties, opens doors for similar digital twin approaches in other complex, real-time decision-making scenarios. Perhaps even in areas closer to traditional software engineering, like large-scale system monitoring, anomaly detection, or performance modeling. So a truly remarkable piece of work, bridging advanced physics, statistics, high-performance computing, and algorithmic innovation to tackle a critical real-world problem. It transforms the seemingly impossible task of near real-time tsunami forecasting with uncertainty into a computationally feasible reality.